Hey, good afternoon, everyone. Uh, Welcome to the class. Just give me a hi if you are watching. Let's see. I mean, I can see only Chaitanya and Vaibhav there. If there are others, just give me a hi on the chat box. Yeah, hi. It's indeed a beautiful day here also. I hope wherever you are, it's a beautiful day there too, right? Okay, welcome to the sixth live stream and class for DD203. And good afternoon, everyone. So, um we'll do one thing. We'll start off today. We are going to discuss a little bit about the casting process itself. I mean, we are going to take a look at the other different types of casting processes, and let's see what are there and what are the different kinds of processes there. And but before that, what I wanted to do is I wanted to discuss a little bit about the assignments that you have submitted, and I am quite happy that a lot of you really put in the effort in learning the software packages, and also going a bit extra mile, and showing the renders and animations and all those kind of things. So let's just first take a look at the assignments. What do you say? Okay, so yeah, okay, right. So yeah, so let's start off with the assignments, right? This is the assignment showcase for the two assignments: the casting assignment, casting modeling assignment, and the Fusion 360 modeling of machined aluminium part. And there are some interesting videos that were submitted in the course, and I thought I would just start off with that. Anyway, okay. So yeah, so Ace, good job on the modeling. Yeah, Ace designed a modular lighting setup. Although I think the dimensions are not quite accurate as to the requirements of as mentioned in the assignment, but it's a fairly good work. The details are there, and I can kind of understand how it would be manufactured. But from the perspective of judging the assignment, it would have been better if you could have shown a little more details on how it would have been, how it would be manufactured. Okay, so it's an interesting work. I mean, it's certainly something that can go into your portfolio, but you need to a little work on it a little more to do that. Okay, it was an interesting assignment. So I have not put all the assignments over here. I have just selected a few which would give me pointers to discuss on on what could have been done better and how you could improve and all that. So this was submitted by Ace. This was by Anshida. Let me move myself to the other side of the yeah, yeah. So this was done by Anshida, and the reason, so first of all, good effort. Okay, you've modeled the whole thing in Fusion, and you made the renders, and it looks fairly good. But the problem is, it's not a design which you can manufacture by machining method. See, one of the requirements of the assignment was you could do the whole thing, you could make the whole design with just methods of machining. Okay, so with just the methods that we discussed in the class last time. Okay, so here, for example, if you can see my mouse pointer, this kind of an angle, right? Getting this kind of an angle is not possible directly. I mean, you would have to have some kind of joinery here. If you want to do something like this, you would have to cut at a certain angle, and you would have to join it in a certain way. So those details need to be shown for the for us to judge properly if the design can be manufactured. So that kind of eye for detail everybody should build, right? So this one lacked that in that front. Okay. And yeah, I was really happy with Chaitanya's work. Chaitanya, good work, yeah. And the way Chaitanya presented his whole thing was also very interesting. He made some initial mock-up models in Fusion to show the ideas, to show the 5 different ideas. Some which he could not make. He tried to do like very rough, mock-ups of it using whatever material was available to him. So I was fairly impressed by that. And finally, the design that he submitted was also very interesting. This is like a coffee maker, a percolator, if I'm not wrong. So the idea is that you'd put coffee in one of these containers, the dry coffee powder, and then you'd fill one of the bottom containers, I think, with water, and it would heat up and it would percolate through the coffee, and you would have like a concoction on the top side. It's fairly interesting, and you could do this with just the basic machining method. So this was good work done by Chaitanya. Chaitanya, congratulations. Yeah. Okay, and also Chaitanya's casting assignment was also very interesting. So one thing that I particularly like to point out over here is the photographs that he took. So these were good photographs. So a lot of the other people, some other students, they seem to have forgotten one of the requirements from the first assignment, the knockdown assignment, was to take good photographs. That is, I will no longer point out that you have to do it, but in the assignment text itself, but you have to do it, right? You have to take good photographs. So this was done in POP, and I mean, it's a gas knob, LPG gas knob, which he had casted using, whose pattern he has made using POP. Okay, so it was quite interesting to see that this kind of details would come into this. And now that this is done, I think what you can do is you just join it together and you pour some, let's say, wax or something like that. You get a mold out of, you get a piece out of it, casted piece out of it. Okay, so this was interesting, good work. Okay, my man Cyril was one of the best renders he had put in, submitted, and this really shows his skill, with the software. And not just that, the design is also very, very interesting. This is like a phone holder. Okay, and just look at the renders. It's quite good. Cyril, good job. Good job. And not just that, I think you guys should talk to Cyril and ask him to take like a session on how he approaches rendering, and if he can share some tips and tricks on how to do such good renders and all that. No, so Cyril, if you are in the chat, then you can say hi. If you are not there, and if you are looking at this recording later on, you try to teach the other classmates how you've done this, how you approach this, right? It's a phone holder. It's very interesting. It can be entirely machined. So if you can see my mouse pointer, so these 3 legs are cut from a stock of hexagonal, the rod that I gave, the dimensions that I gave. This top is also from that piece, and there are some joinery details which can be improved. I saw the model, there are some details underside of it which are missing, but overall really good job. I really loved the renders, and this can directly go into your portfolio. This is so nice. Okay, Devanshi's casting assignment was really well done. Devanshi made like a model using paper. Okay, so she cut and joined paper to show how you would have a casting setup for a simple object, something like this. And not just the casting box, she also made the object would be casted, right? This one. So this was really good quality, and the photographs also were very nice, and it's clear, and you can see the details very easily. And I'm happy that I think she learnt the details of casting a little bit. But there is one comment that I want to make. So there is one thing that I think she missed is the idea of a draft angle. I think it might have been a little difficult to implement it in such kind of a material. But if you see in this model, this piece is what is supposed to come out of the casting, right? So it has very straight edges. So this would, if it was a real thing, then it would not come out because of these straight edges itself. So these straight edges need some draft angle. So if the model had shown that also, then it would have been the best submission there. But yeah, I mean, there's some scope for improvement. Okay, Devanshi, good job. This is Diaz work, and I think Dia made a casting of a Dia stand. Okay, so which was quite interesting, and she made it out of thermocol. The best thing that I liked about it is that she followed the the details that we had discussed in class earlier. Like there is a pouring basin, there is a sprue, and there's a place where the material, the turbulence of the molten material is controlled. There's a blind riser, and then there are vents at the right locations, I think. But in this particular case, you would need vents in all of these locations where there are ribs in the main casting cavity. Okay, so like this. So all of these locations you would need like some vents. And the other mistake that I think Dia has made is this riser. It would not have, generally risers don't have a very small channel leading up to it. So the idea of a riser is that it is a place for the material to overflow. So it would need a fairly bigger channel than this small one, which is of the same size of, let's say, the air vent. Okay, so overall it's a good assignment. However, I would still like to point out that Dia, please take good photographs from next time. This is clear, but I can see that in your bedroom now there's a photograph of a baby, right? And a photograph of Krishna. So yeah, those are superfluous details, right? Anyway, the other one was by Gaurav's both the assignments were quite good. The second assignment I've not put in here, but the second assignment was he designed a ladder which was collapsible. Okay, it's like a modular ladder made out of these hexagonal rods and machined at the end. So if you are interested, you can go and check out his model. So he did not put a render, but the model was done fairly well. Okay, and this is the casting assignment that he did, and he put in some details in this. He's made it, I think, with cardboard. It's very clean, but the photographs can again be improved. The one of the best casting assignments was done by Pranay, and the reason I like this one a lot is because of the stages that he went through. Okay, so first he showed, like, he made a CAD model of the whole thing, of the casting setup for something like this kind of a metal object, and he designed this in CAD, and he showed like a cross-sectional view of how it will be. He gave the descriptions of what are the things that will be there, and after that I think he used wax, if I'm not wrong, to make this whole model. Okay, so this was good effort, really good effort, Pranay, and I really like the quality with which it has come out. Okay, in fact, what I can see is now, if you want, you can actually pour in here something like epoxy, and you can see this, you can make a copy of this object. Okay, so you can try that later on if you want. Okay, that's very interesting. Yeah, so this was one of the assignments submitted. The reason I put this here is because there's a mistake in this that I wanted to discuss. All the rest of the casting assignments, you have like the cope and drag pattern, which was on top and the bottom, right? Here he did it like side by side. This is a mistake, right? You shouldn't do it like this, right? So if you want to cast an object like this, which is like a model of of the twin towers in Malaysia. So you would ideally cast it upside down, and you would have the cope, you would have the drag on the upper part of this, and the bottom part of it, since it is flat, you would have the cope on top, right? And you would invert basically this whole thing. And here he made this mistake, so don't do this. This is the reason that I put in here. After that, Sumira did quite an interesting model. And if she's learned, if Sumira, you have learned this in this assignment itself, it's a really well done job, huh? You have learned the software, and you have modeled something fairly interesting, and you've put in the necessary details. However, there is one thing that there's always going to be a however, huh? Okay, so because nothing is perfect, right? So however, as you can see, the bottom, this thing is a bent piece of material, and if you consider it as thick as the hexagonal rod, this is like a fairly very thick piece of material. Okay, and bending this would be like a tremendous effort. Okay, so it's not a good idea to bend something this thick, okay, unless it's totally unavoidable. Okay, and besides that, bending was not really a machining operation that we discussed. Okay, so besides that, I think it's the rest of the details are quite good, except for this one small area where is in the top, getting this kind of a curved, let's see the video once again, design the product itself. And even in the casting assignment, he made like it's a paper mache kind of a model, and he made the whole patterns and all of these details in paper, and then showed the casting model. However, my my recommendation to Tejas there are two recommendations. First is, I think you should really think about the work that you're putting. The effort, I have no doubts about the effort that you've put in, I can see that, but थोड़ा सा गड़बड़ चले गए कहीं पे, क्योंकि दो चीजें हैं कास्टिंग वाले असाइनमेंट में. इफ यू सी, देन there's some problem with the photographs. Naturally, it's not very clean, and it's not very present, it's not presented well. The second thing is, it's a little, the model itself is a little dirty, slightly a little dirty. So for assignments such as this, where you are visually representing something, you should aim for finish. Okay, good finish. In the product itself, this is like a stand for a pot, I think. Okay, there is some major problems. I think one of the other designs would have been better, but this one, like as I said, bending, first of all, something like this, something this big, this thick, bending something like this would be very difficult. Bending something like this to a very sharp angle, which you see here, right, that is even more difficult. It needs like some major jugglery. And besides that, there'll always be seams when you join something like this, when you bend something, make a roll, and you join it, right, there'll always be seams. You should aim to show such details. But then again, bending was not really a category of manufacturing processes that we discussed. So yeah, overall, Tejas, good effort, but thoda next time when you do your projects, you should think about these details. You should think about the details of the product. Okay. And Anisha, I think she made like a writing instrument. I'm not sure what this is. This is like a very weird thing, but it fulfills the requirements on the assignment, and she submitted this kind of a interesting video to show what it is, and it's good. Yeah. Okay, but the functionality of it is not very clear to me. Okay, right. Well, Gyan, if you are there, I don't know what was this, man. So Gyan made like a suicide spoon. Okay, first of all, man, that is a very touchy topic. Don't go that side, right? And the second thing is, I mean, I don't understand the purpose of it, right? Anyway, the as far as the assignment goes, this kind of a spoon model, it can be manufactured using the raw material that was given. However, I would have been more satisfied if more effort was put in, not on developing the video but the product concept. Okay, so yeah, Gyan, maybe next time you spend a little more effort on the model itself, right, rather than this thing. This was by Manu. Okay, and again, lot of effort. I'm not too sure if this was entirely modeled in Fusion, but uh, it seems to be, right. But the render is not very clean, Manu. You need to because it's metal and it's on a black background. Although I like the idea of the product, right? So you would have slices of the hexagonal rod. It's a different way of thinking of how would you manipulate this kind of a raw material. So it's interesting, but there's some things are presentation it leaves a lot to be desired. And also, I'm not too sure why these kind of cutouts are there. This was not clearly explained in your presentation. And yeah, I mean, you need to work a little more on your presentations. Okay. Madhurya did this salt and pepper shaker. It's a simple product idea, and it's a simple design also, and that is why I liked it. Okay, so you could actually just take the same kind of raw material that was given in the assignment, and you could easily make something like this. Okay, it's a very nice execution. Okay, so good job, Madhurya. Mayank made like a knife out of the hexagonal rod. Well, it's a good assignment considering the experience you got from Fusion 360, but there are lots and lots of details that you've not considered, especially from the direction of how would you make it. Okay, so yeah, Mayank, I think you need to review these manufacturing processes a little more critically and understand how they would be applied. Okay. Meghna made this was one of the more unique products. It is like an egg yolk separator. Okay, and the reason I like this one is because this shape at the front, this was very interestingly done. So the idea is that you would cut the hexagonal rod, axially, and you would get these 6 pieces, right? And these 6 pieces separately would be machined out and joined somehow. That joinery details Meghna has not put in, but it was an interesting thing to see how you would manipulate some raw material that is given to you. So that's very creative is what I felt. Okay, however, it needs a lot of details to really show how it would be actually made, right? And those details is what gives the product life. Okay, right. And then this was by Niranjan, again a very simple product. It's an interesting idea. It's just a pen holder, but I really love the renders. I think what Niranjan did was he modeled it in Fusion, and he went to Blender to render it. So Blender has like a very good rendering engines, and with that you can get these kind of very interesting background effects and all of these rendering effects and all that. So good render, good effort, but I want you to modify this a little more and show what else can be done. So right now it's a little too simple is what I felt. Okay, and this one was by Pranav. The idea is very interesting. So the idea is that this is like a clothes hanger. Okay, if that is the thing. So you would have these hexagonal blocks just, yeah, on the wall, and you could pull one or two of them out and you could hang your clothes on that. So it was quite interesting to see this. However, there is a problem, Pranav, is you can't really assemble it. Okay, right. Okay. Arjun, yeah, welcome. Don't worry about that. Okay. So right. Uh, Next, I hope the sound and all everything is fine. I mean, there are no echoes and no dropped frames or something like that. So if there is something like that, just give me a heads up in the chat box. Anyway, Pranav, overall good job. But I think you when you are modeling, no, you have to think about how the product will be assembled. So right, for example, in this model, the backside of it, right, so how it goes into the product, right, that it will never go in because you model it in this way that it you can't fit it together. Okay, so those details need to be there, but it's an very interesting idea. Okay. Okay. Right. And this one is by Pranay. It's like a phone holder, and he's shown it how he would cut and machine these rods and join it together, and it will become a phone holder. How it is a phone holder? You basically turn it on one side and use it, and it's obviously it fulfills all the requirements. But I felt it was a little bit of an overkill, firstly, and the second thing is I think you should have manipulated it a little more creatively. I mean, there are a lot of other things that you could do from this raw material, right? You could simply, first of all, take it to the lathe and you can make a rod out of it. So if you wanted a rod, you could do that. And manipulation of the raw material, you did not really consider that part. However, it fulfills all the requirements of the assignment. So overall, good job, and good that you've learned fusion also, right? This one was by Prasanna, and it is the most overkill cup holder that I have ever seen. And the idea is that you would have these kind of arms and you can lock the cup in place. Okay, Prasanna, good job on the modeling part of the things, but yeah, it's a little funny, I think. Okay. And finally, this one is, I think, by Priyanshi, and this is like a Halloween candle set. Again, the problems are there, that how would you assemble this, right? So how would this bottom part join to that pedestal? Okay. So those kind of details need to be there. Although I think in the presentation Priyanshi did mention these kind of details, but it was not entirely adequate. Okay, but the render is so nice. It's so appropriate for the time. I think it's October, and yeah. So well, it's good that you went that extra mile to make this kind of a render. I don't know how much time it took for you to make this, but yeah. Okay, well done. In terms of the technical details of the assignment, not up to the mark there, but in terms of the presentation, it's okay. Okay. Right. So now let's come back to our course, and yeah. Before that, if you have any questions, you can ask me. If you have anything to ask, and yeah. If you don't, then we go forward, right? So, and today what we are doing is we are taking off from where we left off last time. We do have a missed class, so we will try to cover it after the next module is done, and we'll see how we can cover it. I'll send the communications. Right, before we go there, let's do one thing. I wanted to show you the tally of the assignments. Okay, let me just put it in the second screen and I will show you. Right. So, yeah, well, let's increase the sizes a little bit. There are a few people who have not submitted any of the assignments, and Amir and Anirudh, it's going to be very difficult for you to catch up to the whole thing, because it's not easy to do all the assignments in one go. Okay, the first thing is, Hardika, no, the next module is not in November. The next module is on 15th, if I'm not wrong. 15th, 16th, and 17th of October. And after that, the next module is in November. Okay. 16th or something. So we'll have some time till then. So what we will do is, I will so whatever assignments that we will have, I will give you that in this module, and you can submit it after the next module is also over. Okay, anyway, uh, so yeah, Ace, the technical details of how you would export something like that, I will not really be able to go into those details. So what you can do is maybe search for some of the tutorials available on YouTube, and or you can talk to somebody like Niranjan or Cyril to get an idea of how they accomplished what they did, right? So, but nonetheless, that does not absolve you from, not submitting the rest of the assignments. Please, Ace, you have to submit all of this. Right. There were a few people who had some issues in their family, because of which they took some extensions. So for them, I have given some specific deadlines. Please submit within those deadlines. Besides that, I think most of you have submitted the assignments, but I mean, yeah, let's see. This part of the class, there is something to be there. Raj, you have not submitted the past three assignments. Sanay has not also submitted, and Sarvari also. Uh, I don't know what is happening, although I do not want to presume anything right now. But if there are some issues that you are facing, you need to come back to me, and you need to tell me what are the problems that you are facing, and we will take a judgment. So, Vignesh, Vignesh, you have not submitted M1A2. I do not see it in your folder. Okay, if you have, let me just check on my side once again. Just give me a second. Yeah, Vignesh, I see your assignment. Okay, I will update that. I may have missed that. Okay. Right. Okay. Uh, Sanay, let me just check yours also. No, Sanay, your folder has only the product knockdown assignment. So if you have submitted, I don't know where you have submitted. So it is your responsibility to ensure that the files are in the correct places. And in case there are some, so as I said, I generally, after the deadline, I'll take probably around that week's time, I'll kind of go through the assignment. So within that time only, you need to see if everything is right. Okay. Okay. Yeah. Yeah. Please, whoever has not submitted, I mean, I will not be able to give you, I will not be able to evaluate you out of full marks. Apart from those maybe who have taken extension. But nonetheless, since all of the evaluation, all of the grading of this course is based on the assignments, you have to submit it. Okay. Otherwise, I am not sure how will I grade you. Okay. Anyway, So this Excel sheet is there in the folder, in the assignment submission folder. If you want to take a look, you can go and take a look. The ones that I've bolded are the ones that I liked. Those were interesting assignments, even if I have not, discussed it. Uh, it's it's there for you, so you can just go and check all these details. Okay. Okay. Yeah. Yeah. Anyway, so let's move on and let's come back to the class. Right, Surya. Surya, yes, I have not. I forgot to put in the details of you taking an extension. Okay, so I will put that, but please consider submitting the assignments on time as per the extension given to you. Okay, so let's move on into the casting phase. Right, so we were discussing about how what is the importance of draft angles, and we were discussing about the design considerations that you need to be you need to think about for casting. Okay, and we were primarily basing it based on sand casting, but it is the same thing. Okay. Uh, yes, Surya. Surya, now if you have access to the folders, then you please submit it in the folders. Okay, mail is quite difficult for me to, go through and search for these things. Okay. Uh, Vishwa Prasanna, welcome. You're not in this class, but it's good to have you here. Okay. Anyway, so let's just discuss with the class, with the casting details. Let's go forward and let's see what we have. So we discussed about the parting line, and we discussed how having a straight parting line is a good idea for casting, because it creates because an irregular parting line creates unnecessary stresses on the die itself, so on the sand which needs to be there, right? Okay. And we discussed about how you can cast a square with all right, all edges 90 degree, all faces 90 degree to each other, right? So yeah, so these were the images, and then we discussed some of the design considerations for casting. Okay, and today I want to start off somewhere here. Okay, and this we had hastily discussed a little bit, and the idea is that uh, see, casting is there are two things that you need to consider in casting. Okay, when you are designing for casting, one is how will the material flow from the place, the gate, to the extremities of the cavity. Okay, and for example, let's say if this is the part, if this is a part, then if the gate is on this end, at one end, then you would have to kind of visualize how the material will flow throughout this whole thing and how will it reach there. And if there are some problems along the way, like turbulence to the in the cavity, or if like for example air bubbles accumulating at some position, you need to consider some of the design things, like adding a vent in the right place and so on, right? So that is the first thing, the flow of the material. The second thing that becomes very important is that the thermal management of it. So by that I mean, when the material is in molten and when it comes down to the when it solidifies, it loses a lot of heat, right? And you need to be able to manage that heat, number one. And the second thing is that when it cools down, it shrinks considerably. So you need to be able to think about how will this when it is shrinking, from where the casting cavity will pull in material. Okay, and that is the main thing to consider when you are placing a riser. So let's say if this part, let me take a pen. So let's say if this part is the casting in question, you have to analyze it based on the thermal mass of the casting, right? So here, since this is a very large volume compared to this, right, the material that will be here will take a little more time to cool. Okay, and as the material, if the material takes more time to cool, that means its rate of shrinking is a slightly different than the other place. Okay, let's say for example this place, right? So when this is shrinking, it will try to pull in material from this side, and if there is some scope, try to pull in material from this side. So, and that's why you should always try to put a riser where there is a larger thermal mass in the casting cavity. So here this is a bad design of a casting cavity where the riser is being put in near the lower thermal mass of the cavity. And the idea is that now when this one cools, right, it will try to pull in material from this side, but since this has cooled more than this larger area, this larger volume, right, this has solidified. So what will happen is that at this junction, there are chances that there is a small cavity which is entirely vacuum which is created. Okay, so it's not being able to pull in material because the material is not molten, the riser is over there, and this is shrinking, and because of that you would have a small area here where there will be a cavity. Okay, and this is a shrinkage cavity. So the same concept is shown in these images also, this one and this one. Okay, so delving into that a little further, this diagram here, wait, where's my mouse? Right, so this diagram over here, right, so this shows you the isotherms. Okay, so I didn't want to use this word, but the idea is that if you take a snapshot, a photograph of the part of this part when it is cooling down after it has casted, then there'll internally, there'll be these lines. Along these lines the temperature is the same. Okay, so these are imaginary lines. Okay, so these along these lines the temperature is the same. Okay, so and as you go in, then you will have more and more molten material and the temperature will be more higher. Towards the edges the temperature will be least, since it is the place from where the heat is being lost. Okay, right, so look at these places, look at this design. So let's say you have this kind of a design that you want to cast there, or there is a portion in your design which looks like this. There is a straight area and there is a perpendicular area to that. And what happens in such a thing is you have this small zone which is colored in a red circle. This has a larger volume than these areas. Okay, because so you can say that this entire area will cool down much slower than these areas over here. So because of this, there are chances that a cavity can form inside here. Okay, and what you would do is you would generally think about solving that beforehand itself in the design itself. So you can solve this particular cases problem by having a hole here, okay, where no material will go in, and the way to do it is probably by a core. Okay, so if you put a core over here, no material will go in, and now all the other places around this core will have more or less on an average a similar kind of dimensions as the other places over here, and because of that there will be no part of in the casting where there's a large thermal mass in very close to a smaller thermal mass, and that is how you would solve these kind of problems. And similarly, one of the thumb rules based on this is that you would try to put in large curves wherever possible. So here, these, instead of these sharp angles, sharp transitions, you would always have a gradual transition. So that way you would not have these large area where a large amount of molten material is accumulated, but rather a flowy kind of design where the material would flow from one end to the other, and that is what is being highlighted in this slide. Okay, right. So to solve the problems arising, sometimes it's not possible to completely eliminate some areas of design such as this. To solve that problem, people generally use these things called chills. Okay, a chill is a piece of metal which is very close in composition to the molten material that you want to cast. And what you would do is you would put it in the casting in the sand, in the mold, and the idea is that once the molten material is flowed in, since this is already solid, this will be a location from where the cooling of the whole thing starts. Okay, so this is one place where the cooling starts, of the cooling of the molten material, apart from, let's say, the surface. So from the surfaces also some amount of heat is radiated, and because this is solid, some amount of heat is radiated or absorbed by this, and because of that some cooling can start from this location. Okay, and because of this, this will solidify in a different manner had this piece not been there. Okay, so like this, for example, if you have this kind of a design feature where it's a right angle and there's a fillet on one side, this portion is a much larger thermal mass, and this may have a chance of having a porosity internally, and these internal porosities are some of the most worst thing that can happen in a casted part, because you can't really see it from the outside. So the way you would solve for this problem is you would have a small metal piece, something similar to that fillet line, and then when you cast the whole thing, the material, instead of cooling from just the outside and coming and the center of it being hottest when it is getting cold, the cooling will start off from the chill also. So it will start off like this, right? And it will lose heat from this side and this side and all these places also, but it would also lose a lot of heat from this place where the chill is put. Okay, later on, after the casting process is done, this chill becomes part of the casting. Okay, and this can be machined off as required. So these are other places where such a design thing can be put in. The shape of the chills are also quite different for different applications. Okay, some are like this, some are the shape of springs and all, and it depends on the kind of circumstances that you have. Okay, similarly, let's say in such a scenario where you have a casting, this is the casting, and right, so this part is the casting, and you have, because of the shape of the design, you have this large area which is a much higher thermal mass than, let's say, these cross sections. Okay, and because of that, there are chances that there's some porosity may happen at this location. So to solve that, they put in a chill at this end where the molten metal touches, and there's a much more rapid cooling from these sides. Okay, then had it been there, that there was no chill. Okay, so this is one way in which such problems with casting is solved. Right, so the next thing is how thin can you make a casted part. Okay, for sand casting especially, these are the kind of thumb rule dimensions that are there. For example, steel, for example, steel 5 mm is recommended. Below 5 mm it becomes very difficult, because when the material flows, chances are that it will solidify as it is flowing, and you'll have design defects in casting such as misrun. For aluminium, you can go to as low as 3.5 mm. Okay. Hardika wants me to explain the chill part again. Okay. I If you have a specific question, Hardika, maybe that you can ask, because it will be quite difficult to go and explain the whole thing back again. Okay. So if you have a specific question, maybe you can type in there and I will explain it. Okay. So similarly, there are these other, materials. So this is the minimum thickness that we can achieve, we can technically achieve when we are doing sand casting of, let's say, steel. Okay, 5 minimum thickness, but it is desirable that you should have something around 7 or something like that. Okay, 6.5 and yeah, similarly for others. So this is like a thumb rule that you should follow. Let's say if you are doing something called die casting, then you can go to a much lower thickness. Okay, as you can see, aluminium die casted parts, you can make it as thin as 1.5 okay, and 1.5 is fairly thin. If you have a scale at hand, then you can see how thin is 1.5 you can get a visual idea about it. Okay, anyway, let's move forward. And so this I don't know if I've told you before, but war has always been like a motivator for most of the manufacturing processes, because you would want to make some things. Generally in wartime, you would want to produce things much faster and in a more reliable manner. And this one was, I think it's called the Rothman's cannon, and it is a very interesting case study in casting. And these cannons were, I think, used during the American Civil War time, and the cannons that were used before that were, but I'm not sure whether it was used in the Civil War time. But yeah, anyway, so that is, apart from that side, the important part that we should learn here is the creative way in which the manufacturers solved some interesting problems with casting. Okay, so when you would cast some large pieces like this, right? Right. Okay. So when you would want to cast some things as large as this, so generally what they would do is they would make a cavity on the ground. So this is a diagrammatic representation of how it was casted, right? So you would have like the cavity in the ground, and you would have a core from the top, right? So you'd pour material from the top. Now the problem earlier, before this particular cannon came about, was when you would cast, the I would draw here. So let's say this is the Rothman's cannon's casting process, but let's say in a typical process, you would have just a core here, right? And this is the part where the material would go in. Okay. So molten material would go in here. So what would happen is that this outer surface would cool down at probably the same rate as this inner surface. So these inner surfaces is the place where the cannonballs would be held, right? So the cannonballs would be held like this, and because of this way in which the material cooled, you can imagine that there'll be a place here at probably the center of this whole thing, where there are chances of these porosities, these design defects, casting defects coming into existence. Okay, and because of this, the earlier cannons were fairly unreliable. That means they would have, once a few rounds were fired, cracks would appear, and the cracks would easily traverse through the surfaces, because this internal part was almost as hard as the external part. If you imagine the grain structures that would happen, uh, at a cross section of this. So let's say this is the cross section of one of the walls. This is the place where the cannonball would lie, and let's say this is the cross section. Okay, I took a very small sample from here. So you would have small grain structures on the edges. Okay, and it would probably be the same thickness on both sides, and you would have these larger grain structures at the center because it got the amount of time in which it cooled down, the molten material cooled down at this location was much higher. Okay, so and also chances are you would have like casting cavities and casting defects along these central portions. Because of this, the cannon would crack like this. Okay, because this surface was almost equally as hard as this. So the way Rothman kind of solved this idea, so what he wanted to do was he wanted this internal part to be much harder and much stronger. Let me clear that drawing out. So, and let me remake it. I want to do it with this. Okay, let me just right. Okay, give me a second. Okay, so what you much better. So let me make that again. So what he did was, what he wanted to do was, he wanted this portion, okay, to be much harder. And the way you do something, the way you make this material much harder is have large or smaller grain structures at this location. Okay, and there should be a significant amount of it at this location. Okay, then let's say here. Okay, so here there may be some amount of some layers which is much harder, but he wanted essentially something like this. So what he did was quite ingenious. He made this kind of a rod, which I don't know, you can see here. So he made this kind of a rod as the core, and inside the core, no, you would flow water. Water would flow in and it would come out. Okay, and because of this, the amount of heat that was absorbed by this water, because of the amount of heat absorbed by this water from the molten material, the cooling would start off here. Okay, and it would go in towards the outer edges. Okay, and this way it would be much stronger on the internal part where the cannonball would be there. You can now imagine if the cross section of the cannon to be something like this, right? So now internally this is much harder because of the cooling starting off from the center, right? So this is an example of a chill which was used to solve a major problem. Okay, and this simple thing that he did, or I don't know, I don't think it is simple, it's fairly difficult to execute something like this, but nonetheless this simple idea that he had, that cool this part at a faster rate than you would cool the outer surface. Okay, just that simple idea resulted in a cannon which was so much more reliable, and now these cannons naturally I think they are decommissioned and replaced by more powerful equipment. But yeah, so this small case study showed you like that how that intuitive understanding of casting and the cooling of molten material achieved some really decisive change in a social environment. Okay, if that makes sense to you. Anyway, right, so how would they cast the fuse holes? The fuse hole, naturally you would use something like a core and all that, Gaurav. You would use maybe in this one you would have, so maybe it's not shown here, but you would have a core that goes in from this side, and whatever details are there needed for that kind of a design would be there in the core. Okay, so that would probably be the way in which it would be done, but I'm not entirely sure. But yeah, I'm guessing, I'm taking like a guess. Okay, so anyway, yeah, so Hardika's question, let's come back to that. And I think what you want to know is you don't understand the junction, how the junction may get porous in figure C. Okay, let's go to figure C. Yeah, okay, okay, fine. Yeah, so that's a specific question which I can answer. Uh, so consider this part, okay? Uh, so let's say all of this is a cylindrical piece, and this here the cross section is like this, and similarly the cross section is the same, is cylindrical. Now at this location, you know, imagine the material that is there over here, okay, because of this whole thing. So if I want to draw something like this, it will be right. It will be something like this, okay. So this is the three-dimensional, rough three-dimensional interpretation of this diagram, right? So what would happen is that, can I do a different, yeah. So what would happen is that if you see closely, then this area over here where this part is joining, right? This area is much larger in volume than all of these other areas, all of this area, you know, right? So what would happen is that, think about how it cools, right? It starts cooling from the surface, okay, and wherever, if it's a uniform thickness, if it was just a rod, okay, it would cool at the surface, and as it goes to the center, it would have smaller grain structures at the surface, and it would have much larger grains at the center, okay, and that's how it would cool. Why it would cool this way, if you ask, because let's say take a certain time after it has started cooling, right? What would happen is that the amount of temperature difference between, let's say, the surface and the environment, if let's say this is 30 degrees, and if this one is, let's say, 1500 degrees, you can imagine the amount of temperature difference, right? It's huge. And so this temperature difference enables the loss of heat from the surface at a much higher rate. Now think about this small area at the center. The temperature that this small area, imagine this layer, this cylinder, imaginary cylinder at the center. The surface of this cylinder and this, just the temperature outside it, is not that high, right? So the surface is probably at 1600 degrees, and this part just outside it is probably at 1200 degrees after it had started cooling a little bit. So as you can see, it's not much of a temperature difference. So the rate of cooling of the material at the internal cavity will be much slower, and because of that, the grains would have much more time to coalesce and form larger, structures. However, in something like this, let's say, what happens is that you will have the same kind of, you know, action going on, but imagine this area. So you would have this large ball where the temperature difference between this surface and the just the area outside it is not too high, okay. So as it cools down, so this part has already solidified, okay, so that means it can't move, and this part is solidifying, right? So that means it is shrinking. So when it is trying to shrink, it is trying to pull in material from all these other locations, okay. And because of that, as it shrinks, right, there'll be a tension in between these layers which is getting solidified, if that makes sense, and at some point, no, that layers would split and this kind of a cavity might get created. I hope that makes sense, okay. And because of that, you know if there was no chill over here, you would get a cavity at this location. Now if you put a chill over here, what happens is that instead of the typical process of solidifying from all the surfaces and the central location not having enough temperature difference, it would start solidifying from here like this, okay. So let me clear it out again. So let's take, so this is how it will solidify. So here probably at a certain time it has solidified this much, it has solidified this much, but just because this chill is there, this part has probably solidified this much. All this area has lost its heat to this chill. Okay, and because of this kind of a solidification process, as you can see, there are less, this part, if when it shrinks, no, it is able to pull in material from all of these locations where it is still molten, and so this kind of a cavity, this kind of a casting defect cannot form over here. Okay, so that is the idea of a chill. Okay, I hope that answers your question a little bit. Yeah, well, unfortunately, Gaurav, Chaitanya, I have not seen Kranti, or is it that Manoj Kumar film? Maybe it is, right? Yeah, I don't remember it. Yeah, well, okay, that's some trivia for you. Anyway, so let's move on. And although casting seems like a very bare bones process, and it seems like it's not really something from which you would get really aesthetic parts, but look at this, what designer Geckler Michaels has done. Okay, I hope I'm pronouncing that name right. And the idea is that, so just look at, this is the chair that he is designed. Okay, so this is the this is made in aluminium, and this is sand casted, and as you can see, when the chair is inverted, no, you can see these locations. Okay, this is the sprue, this is the place where the molten material was poured in, and these are the places, these are legs, and these are the risers. Okay, the legs work as risers. So you pour in the material goes into all of these locations which is needed for it to cast, and the rest of it, it comes up to these risers and fills up, showing that the flow is, the material has reached all of the places. And these themselves, instead of typically like how we think we would cut off the sprue and the riser places, instead of that, what he has done is that he has used this as the legs themselves. So I thought that this was like fairly ingenious, and this was a great idea, and it probably saved him a lot of material also. Anyway, so this is a design, and this, what you see at the bottom corner is, okay, let me move myself to the other side. Right, so what you can see here is a simulation of the casting process. It is possible to simulate casting. Okay, and you could do that in for example, this one, I think it was done in a software called Magma Flow, and you could do that in something called ANSYS. There are a lot of other software packages which enable you to see how the flow happens and how it cools, and you can actually get a good idea of how the casting will happen. So in this one, for example, after the whole molten material is poured in, you can see the red locations are the ones which are slightly lower temperature, and the bluer locations are even lower than that. So this part cools down faster, and the yellow part is much higher at a much higher temperature. So this scale is in temperature, degree centigrade. Okay, so yeah, so that's the idea. Anyway, moving forward. So that's about it for casting. Okay, so let's take a look at some other forms of casting, and we'll just go a little faster from here on out. Okay, if you have yeah, Chaitanya, thank you for that. Okay, anyway, so let's move on to the next manufacturing process. Just a second, I will increase the desktop audio.
Niagara Investment Castings and your interest in learning more about the investment casting process. These precision castings are sometimes referred to as near-net shape castings, since they can often be used with little or no subsequent finishing operations. The entire
So what we are going to see is this process called investment casting. Okay, and this is like a different type of casting process. I think one of the most different types, and but it is one of the oldest methods. And now, with as technology has progressed, a lot of things are automated, but you could see the process and see how I shouldn't say rudimentary, but how simple the process, the steps are. Okay, so let's take a look at this video.
manufacturing process starts with wax patterns produced from injection dies. The defining characteristics of an investment casting, including its smooth surfaces, dimensional accuracy, and high degree of detail attainable, can be attributed to these dies.
So as you can see, let's say in traditional casting processes, it would be all nearly impossible to cast this in, let's say, steel or something like this, only because these features that are there, these are quite thin for such a process, for sand casting to work. The other thing is that if you notice carefully, there are like significant amount of undercuts that are there. I will not explain undercuts. I think you should know. So undercuts are these places where you would probably need a core to get some features like that. Okay, and so as you can see, this part, it would need a lot of
This is repeated for every part that is required.
So yeah, so the first step of investment casting is to make a wax pattern. So these pieces that you see over here are probably part of a handle, okay, a sturdy handle, okay, which is going to be made in metal. So unlike sand casting, the pattern that you make is a one-time job. Okay, so you make one pattern, and that you can use multiple times to make a cavity in the sand and fill it with molten metal. Okay, however, in investment casting, for each part that you would need a wax pattern. So this is the wax pattern which is made. Okay.
However, multiple cavity tools are used for high volume jobs to help with costs and increase productivity. The degree of internal detail possible with an investment casting is one of its most versatile characteristics. This detail is formed using either simple pulls in the tooling or by using soluble wax or ceramic coring techniques for more complex internal detail. For prototyping or very short runs, purchasing of production-oriented tooling is not always economical, so we offer the option of special printed patterns produced using stereolithography from 3D CAD data.
So again, in the first one also we saw how additive manufacturing is being used for sand casting, and in this one process also you could use additive manufacturing, that is 3D printing methods, to make these wax patterns. Okay.
Once the wax patterns are produced, they must be assembled to a feed system called a sprue. The sprue is made from reclaimed wax and designed to not only hold the wax patterns, but also engineered to form a sufficient pathway. Metal flows through the mold during casting to produce a sound and defect-free component during solidification. With the waxes now assembled to the sprue, we have completed what is called a tree.
So as you can see in this piece, they are trying to cast these impeller blades for probably a pump or a blower. Okay. Yeah, so these blades they are trying to cast, and what they have done is, once the wax pattern is made, they have assembled it onto this other piece of wax. This square piece is also wax. Okay, they've tried to assemble it in a manner which resembles like a tree, so that's why it's called a wax pattern tree. Okay, and yeah, so let's move on.
To transfer the
shit, what happened?
Exact detail of the wax pattern to the casting. The trees are encased in a seamless ceramic shell mold. It is formed by robots dipping or investing the wax into a slurry, drying the tree and repeating. This builds up 3/8 to 1/2 inch of ceramic around the tree. It is this ceramic shell or mold which will receive the molten metal during casting. The first coat is called the primary. It forms the innermost surface of the mold. For that reason, it must be carefully applied in very controlled conditions to ensure the quality. Gradually, additional layers of increasingly coarser secondary ceramic layers are added, and the completed shell takes form. The next step is to remove the wax.
Okay, so before we go to the next step, let me just rewind it just a little bit. And so after that wax tree is formed, what they would do is they will coat it in a refractory material. Okay, here they are saying ceramic, and typically ceramic is used. Okay, the idea is that once this wax pattern is made, if you make that shape, if you coat it with ceramic, and if you fire the ceramic, you know how you ceramics are made. So ceramic, you would once you would make the pottery, you would make a pottery, you would fire it in a kiln, you would put it in an oven, and you would heat it up to a certain temperature called glassification temperature, where it would solidify and it would get the properties of ceramic. Okay, so this is the slurry, this is the mud which is before it becomes that pot. Okay, so first you would coat the wax tree in a thin layer of mud, and you would coat it again with a slightly thicker layer, and eventually you would coat it with
Layers are added, and the completed
with a powdery form, almost a powdery form called stucco. Okay, and this makes, let's say, think about what happens. So the wax pattern is there, and it is coated in subsequent layers with this material, which will become, let's say, ceramic. Okay, when it is fired.
shell takes form.
Okay,
The next step is to remove the wax patterns and sprue.
now once you fire
We
it,
do this by inverting the shell into either a steam autoclave or flash fire dewaxing furnace. The wax melts and runs out, and the shell is now complete and fully self-supporting.
so yeah, so now think about what has happened. So once you have this kind of a mold that is there, the wax is inside, right? Naturally no metal can go in, right? Till now the cavity hasn't been formed, so you would put it in an oven and you would heat it up, and because of that the wax will either evaporate away, or you can melt it away and remove it from the whole ceramic piece. And now the what has happened is, internally there is a cavity created. Wherever there was wax, there is no longer any wax, and it is just a cavity made out of this material, this ceramic material. Okay,
When the shells are scheduled to be poured, they are reheated to approximately 1700 degrees to further condition and strengthen the ceramic shell. They are
this
now
is the
able to withstand the
firing
thermal
stage.
stress they must endure during the next stage. While the shells preheat, we prepare and melt the metal to be cast. When at the proper pouring temperature, the chemistry of the alloy is checked, and the molds are filled with the molten metal. The metal completely fills the cavities of the mold, taking on the geometric shape which will form the outer detail of the cast component. Inside the cavity, the molten metal also surrounds any cores, which will impart the same detail to the internal geometry of the casting.
right? Okay, let me go back to this part. Yeah, so we'll Shirsha, yes, Shirsha is right. Dokra crafts are a type of old Indian crafts that are there, I think, in West Bengal, lower West Bengal region. I may be mistaken, but yeah, somewhere in West Bengal. So the idea is that they make this very intricate, detailed murtis okay, figurines in wax, and then they do this same kind of process, and they would fill it with I think brass, a type of crude brass, and you would get these beautiful intricate details murtis. Okay, so that tells you how old this kind of a process is. So yes, thank you Shirsha for bringing that up. Pranay, the wax does vaporize in some variations of these processes. People would heat it to such a high degree that wax would directly vaporize. Okay, yeah.
into its solid form, and the ceramic shell is now ready to be removed from the castings using a variety of cleaning methods, including blasting, vibration, or chemical cleaning.
So now after you have poured in the material and it has cooled down, the process is straightforward. Break away the ceramic outer layer.
The castings are cut from the sprue, and the ingate is removed by grinding. Finally, the individual castings are given a final cleaning to expose the smooth and detailed surface. If heat number traceability is requested, this identification is directly engraved onto each of the castings. The castings are now ready for final processing to the customer's requirements, including heat treatment, NDT testing, machining, plating, or other value-added processes. The investment casting process is an economical manufacturing method that offers many benefits and advantages over competing processes. We hope this video has been informative and helpful, and thank you for your interest.
Right, okay, so that was the process of investment casting, and you could see visually how it is done in an industry. And this one is a fairly high-tech industry, but you can do it in a fairly rudimentary setup also, because it does not need so many specialized equipment as such. Although the more specialized equipment, you would reduce the production time, and you would reduce a lot of these other error prone processes that may be there. Okay, so this is investment casting. This is a visual representation of how it is done. So first, as you saw, there was an aluminum die or a metal die in which wax was poured in, and individual parts or which would later be transformed into metal were formed, and these were connected into a wax tree like this shape is connected over here. Okay, these were then coated with something called investment, which is a slurry of which would later become ceramic, and after subsequent coatings you would at the end coat it with a powder to make this kind of outer layer of this ceramic very strong. And then you de-wax it either by heating it to a temperature where the wax completely pours out, or it evaporates, and then you would fire this cavity ceramic to a certain temperature that it becomes solid, it becomes strong, and it can withstand the heat of the molten material. Then you would pour in the molten material, and finally you would remove the break away the ceramic part by either vibrating it or just hitting it, or just blasting it with some short pallets, okay, or ball bearings, and then finally you would cut off the necessary part, and you would finish to the dimensions necessary, and you inspect and send it in its way. So this is the process of investment casting. And famously, do you know the name of this? It's not Rolls Royce. Okay, it is used in Rolls Royce, but what is the name of this thing? So if you know the name, you can just type in the answer. Okay, and this is how it's made. It's made using investment casting. You would make a wax model, you would finish that wax model, and you would make, and this is a very good image. Okay, this shows a cross section of the layers that are built in, and you can see the layers that are there, right? So there's a thinner layer, there's a thicker layer, and slowly, and at the top there's like a stucco layer. and once this is fired, this is the what is seen. Okay, yeah, you guys are right. It's called the spirit of ecstasy, and this adorns the hood of every Rolls Royce that is there. I think there are some variations to this in different Rolls Royce cars. Okay, anyway, so once this is fired, you can see those layers kind of merge together and it becomes a really solid piece, and this can withstand the temperatures of molten material, and then it is cleaned up by hand. Okay, flying ladies. Yeah, it is a flying lady. Okay, anyway, so it's used in Rolls Royce hood ornaments. Okay, right. So a variation of this, instead of using wax, you could use something like thermocol. Okay, and the best part of thermocol is that it is, if you just directly pour molten material on top of it, you would you know, the molten material would heat and eat away on the thermocol parts, and it would become impurities within the molten material itself. But it's such a small volume. If you're casting very large parts, then this is like a good enough process, right? So you would have a polystyrene pattern. You'd put the sand in. So let's say if this is you want to do it by using sand, you'd put in the sand, and you'd just properly close it and follow all the guidelines and design considerations for casting, and you just pour it in molten material. The molten material will burn away the styrofoam, and it will take its place. Okay, so this is called lost foam casting. And Ace has a question: won't the metal cooling problem still exist, like volume reduction? Yes, certainly. The design considerations for casting are for all the processes that are there, right? So these things about the thermal masses, the idea about how it will flow and how it will cool, the generic defects of, let's say scabs and inclusions and misruns, all of these need to be considered when you are designing for investment casting also. However, the best part is that you can make like really intricate shapes, and you can make thin parts also, okay, with investment casting, right? This is a video of lost form casting. We'll not go through it because it's a very rudimentary video. We can just
for molding.
Show it.
Beads as purchased have a cellular structure.
Before the styrofoam becomes styrofoam, it comes in these small beads which are put into a mold, and steam is passed through the mold, and these beads kind of expand and take in that steam and take up the shape of that cavity. Okay, that's how styrofoam is made. Anyway, this video is there for you. You can go and look at it later on. Okay. Next we come to a different form of casting, and this is called the die casting. And let me just run through the presentation once to see how much is there. Right, so I think we can do this. Okay, let's finish casting today. And okay, so die casting is a process of using permanent molds to cast. So in all of these previous processes that I showed you, the molds were temporary. That means you would either use sand or you would use these kind of can investment casting equal to lost wax casting? Investment casting is lost wax casting because the wax is lost, right? So these are the same thing. Okay. Right, so in die casting, what happens is that you have a permanent mold. You typically choose a material which is at a which has a much higher melting point than the material that you want to cast. So typically for aluminium, this is a very good process because you could make the die out of steel, and aluminium's melting point is somewhere 600 to 900 depending on what type of aluminum you use, and uh, a melting point of steel is, let's say, above 1400 degrees centigrade. So this makes it a fairly good compatibility. And the setup, however, is much more mm, much more technically intensive, if I may say so, right? So the idea is that, so this first one is called the low pressure die casting, and this is like a schematic diagram. It may look very scary, but the principle is very simple. Okay, you have a place where you are holding molten material. Okay, so this is a ladle, and it is lined with some refractory material, so the molten material does not damage the walls of this ladle. Okay, and this is placed in a chamber, and what happens is that on top of this chamber there is this die. Okay, and this whole thing holds the die. Okay, and the die is in two pieces as usual. It will have all the detail, it will be designed with all the considerations of casting, and it closes, and what happens is that it comes down on a pipe is attached to the die. Okay, the arrangement is such that there's a pipe which is attached, and this whole setup kind of comes down to the molten material until the pipe reaches the molten material. Now the setup is created such that this whole area where the molten material is held, no, this is a enclosed area, and it does not, that by that I mean there's no way atmospheric air can come into it. Okay, now once this situation is reached wherein the die is in place, where this die is in the right place, the tube is dipped into the molten material. If you put in air pressure inside this area, okay, I need this again. Right, so this is the area which is enclosed. Okay, and the only access to air that is there is from this vent. So what you could do is, if you pressurize this area, if you have a larger pressure in this area, this top surface of the molten material, you would apply some pressure to it. Okay, this air pressure would apply some pressure on this top surface, and because of this will get pushed down, this level will get pushed down, and the molten material will rise up the tube and fill into all of these cavities in the casting cavity. Okay, and this gray brown gray thing is the die. Okay, so you have a die like this with both the cope and the drag pattern. In the case of die casting, it's called a top and a bottom. Okay, and so here you have, let's say, the cavity, and let's say this is the ingate, this is the place where the material will flow in, and this one is connected to that tube. Okay, so imagine what happens is that if I have enough places where the material can rise up, there are vents and there are whatever risers and all that, whatever material comes in, it flows into all of these locations and it rises up to the top. Now once this has been done, once this is through methods of process control, I can estimate exactly how much time is needed for this much part to cool down. Okay, and once that part is cooled down, I can remove this whole thing, this whole apparatus. I can move up. Okay, I can move it up, and I can open the die, remove this piece, close the die again, come back down again, and start the cycle once more. So it's a very high production rate. There's going to be a very high production rate in this kind of a setup. I will clear this thing and you can see the process once again. So this is the chamber where the molten material is held in. Air pressure comes in, it pushes the top surface of the molten material. Molten material rises up into the cavity. The material in the cavity cools down. This whole piece moves up along with the die, and once that happens, or I think in this case, no, what they have designed is that these are like piston rods. Okay, these will move just the die up, not the this gate. Maybe that is why it's a fairly complicated thing. But what you need to know is that there's like one surface on which the die is connected. Okay, and the die can be this whole thing with the cavity with the die can move up. There's a tube that goes into the molten material, and instead of pushing the molten material, you push the top surface, the molten material flows into the right location. Okay, so that's how low pressure die casting is done. And the reason it's called low pressure die casting is because the amount of air pressure required in this for to make it flow to this die is not too much. Okay, exactly how much, I mean, I don't know that, but yeah, the it's lower than the other process called high pressure die casting. Okay, where you can make slightly thinner parts also. So let's take a look at the video of how this thing is done. Okay, just a second. Right, so it starts off with like reclaimed aluminum. Aluminum is a very recyclable material. Okay, so typically most aluminum products used at least some portion of recycled aluminum. Okay, a majority I think they used recycled aluminum only. Unfortunately, there's no voiceover, so I'll just reduce the music and probably I can talk over it. Okay. So, uh, so let's just see that. So this is reclaimed aluminium, and this is aluminium being melted, and you would take it and you would place it in the, yeah, so this is how the die looks like. Okay, and that's the pipe that comes down. Wait, let me just see. So that's the die that is there. Here in this particular setup, what you can see is that the top half of the die can move up and down. The bottom half is exactly where it is. Okay, and you would close it. As you would close it, this tube comes down onto the molten material. Here in this particular case, the tube is spinning, which I think homogenizes and mixes the material properly, and the tube kind of pulls in the material. Now, so that was the details were not very clear. I couldn't find a better video of the die casting, especially with voiceover. But now we are moving on to another process of die casting, and this one is called gravity die casting. And here, I think it's called cold chamber die casting. Okay, so let's just take a look at how the industrial setup is there. Yeah, as you can see that this is the part, and there are robots which kind of need to be employed to have die casting parts, properly handled die casting parts. Okay, right. Okay, I don't want to see the robots, but I do want to show you the versatility of the parts that can be created. So as you can see, this one is a thin section. There's a lot of variation in the sections, and it is very, very wide. Okay, so it's like almost like a sheet. Okay, with a small, with whatever design features that need to be there, and such a part is definitely possible with die casting. Okay. Okay, right. So I think let's the other type of die casting process is the hot chamber die casting, and this is the kind of machine that is there. And you can see this piece is the part where the die is held, right? So you would press the die, and I think in one of these areas, I think this is the area where the material would kind of flow into that. So it's fairly close to something like injection molding, but with its own variations. So this are two videos that kind of tell you schematically what happens. So this one is cold chamber die casting. I think it is also called gravity die casting, but I'm not very sure. But let's go forward with the typical jargon that is there. Okay. So the idea is that you would have this die, you would have a plunger which pushes the material, and this comes out. So you have a die which is also a fairly complicated construction. It's not too simple. You need things like these small things, right? These are injection pins. These are pins which remove the casted part from the piece, from the die itself. Okay, so there's a fixed half and there's a moving half. And now once the molten material is poured in, the plunger pushes the material, it goes in. See these ejector pins coming forward, and they kind of push the part out of the die. Okay, the same kind of mechanism is used in injection molding as well. Okay, so another cycle just to show you the visuals. Okay, right. So this one is the hot chamber die casting. In hot chamber die casting, rather than putting in materials every time, putting in molten material every time you need to cast, this is automated. You would have molten material in a place where it is being melted, and the plunger itself is connected to that. And the plunger, once it comes down, it's connected with a gooseneck to the die, and the rest of the setup is fairly similar to what you have over here. And it will just come down, push the material in. This whole thing comes out along with the piece attached to that. This is A, this is B, right? The AB is the die name. So the A is generally given to the part of the die which does not move, and B is generally named the part which moves. Okay. Right. Ace has asked a question, but I'm not sure which process is he asking this question for. What if the metal cools inside the tube or other parts? Well, you can ensure the process parameters and the temperatures of the setup in such a way that that does not happen, right? So otherwise, the most common thing that I would ensure what will happen is that the engineer will get fired. Okay. Anyway, so yeah, so this is hot chamber die casting, and this is cold chamber die casting. The same things that we saw. And die casting is really, really versatile, especially in creating this kind of very intricate shapes with a lot of flow and with a lot of intricate details in it. Very famously, these model cars and Hot Wheels and these kind of things where you see metal, very small parts made out of metal is probably made with die casting. Okay, and if it's aluminum, all the more chances that it's there. Okay. Right, so this is one of my favorite chairs. It's not very famous. I don't know why it's not very famous, but it was designed by a designer called Ross Lovegrove. And the way he designed it is he took inspiration from how our bones and muscles kind of join together. Okay, and this kind of intricate details that you see over here in the chair, right? It's possible to get those things from die casting, along with these small, grooves in the seating and all that, right? It's possible to do that with die casting. The holes and all are done later on as a machining process, and you naturally need to do some amount of cleaning processes and all that to make it like this. But just look at this chair. I think I have not seen anything like this, right? So it's very, very nicely designed. And Ross Lovegrove is one of my favorite designers. He's designed some really iconic products and all that, and mostly because he puts importance to form, function, and making methods. Okay, so yeah, you should go check out his work. Tejas is asking, why is it called die casting? It's not because somebody dies. It's because there is the mold. Okay, everything that has a permanent mold, no, it's called a die. It's not called a mold. A mold is typically something which is not permanent. Okay, you would change it, or it gets modified somehow after the process is done. A die is something which is permanent, DIE, right? So that's why it's called a die casting. Let me switch on the lights. Okay, where was I? Right. So very interesting chair, very interesting design. Let's move forward. This one is also a good, example of die casted chair, die casted furniture. As you can see, the thickness of the parts is fairly small, and this Magis chair one uses that kind of feature. And this is a photograph I took of the book. I shouldn't be putting it here, but yeah, well, it's there. What the hell? It shows you this is from that book called Rob Thompson, and it shows you the process in which the Magis chair was done. So yeah, you can see this is how it was die casted, and after that, you could clean it, and this is what it becomes. Okay. Right, so what are the specific design considerations for die casting? Die casting, you should always try to minimize totally flat surfaces or very large flat surfaces, and you should try to minimize the variation in thicknesses as far as possible. Okay, it's always not going to be possible. Like here, there are a lot of variations, but it's still well casted out part. So yeah, so the second thing is that for large flat sections, when it cools down, there are chances that it'll warp, it'll cool in uneven ways, and it'll change its shape. And to stop that from happening and to impart strength to the part, you would add something called ribs, okay, in all of these large flat sections. So like this, these are called ribs. These you can see over here, these are called ribs. Okay. So there's generally a question that I ask to the class: is it better to over design or under design the part, right? So here, for example, I could do away with this kind of a design, but a better design would be something like this, right? So which has like as far as possible uniform thicknesses in wall thicknesses, but I could do away with something like this, right? So why would I choose something over this over this, right? Anyway, so the other thing is vacuum casting. In low pressure die casting, what we did was we pressurized the top surface of the molten material so that it flows onto the die cavity. Okay. Here, however, what we have done is, instead of pressure, we are using vacuum. We are we are using pressure in different manner, but yeah, we are employing vacuum. So the die is connected to this kind of an apparatus where you could create vacuum on one side of it, okay, and the whole thing is lowered into molten material, and the material is basically sucked into the die, okay. So yeah, so this is called vacuum casting process. And after that, these are like some specialty casting methods, and you can, there are many of these. Some of these I have put in, like this one for example is a simple process called squeeze casting, and the idea is that you would pour you would have this kind of a die, permanent die, where you would pour material and you just press in, and because of the the action of pressing itself, the molten material kind of goes and takes the shape of the cavity. There's a cavity which is created. Right. Okay, so here let's see what this video is. I don't remember this one. Let's see. Oh yeah, okay. Wait. I sound. Okay. So this is again.
Highly complex parts can only be made with great effort and difficulty.
So this, we are looking at another type of a manufacturing process, okay, and this is not. This is something like die casting, I should say. Okay.
Using conventional manufacturing methods. With MIM technology, OBE can manufacture complex precision parts easily and inexpensively for its customers. MIM technology is based on a feedstock that consists of metal and plastic and meets the typical requirements of injection molding. The metal injection parts that are made in the first production step are then heated in kilns where the heat removes the plastic from them. What remains are top-quality metal-injected parts which can be used, for example, in upmarket designer products. Companies engaged in medical engineering and aviation also get OBE to make parts of stainless steel, titanium or other materials using this technology.
Right, okay. Advertisement of the company aside, this process is called MIM, which is metal injection molding. So it's again a subtype of a die casting, but it's fairly different in the manner that instead of using, see, naturally there is a die, there is injection molding die, but instead of using something like molten material, you would use pellets or small pieces of metal, okay, metal powder or something like that, pellets of metal, and these pellets would be mixed with plastic, and it would be run through a injection molding machine, okay. And what would happen is something like this, right? So you would have a metal powder, you would have a polymer binder which is plastic, you would mix it to ensure homogeneity, you would make you would ensure that it is of the right size to push through an injection molding machine screw, okay. And basically that's the process of granulation, which is making it into a small grains. You would have something called a feed stock, okay, which is the powder which goes into the injection molding machine. And the injection, after the injection molding machine, what comes out is that a part made out of metal and binded with plastic. So it's a metal plastic kind of thing. There are two ways in which you would remove now the next step would be to remove the plastic entirely from this part to make it metal part, okay. So what you would do are two things. One is either you run it through a chemical bath to remove the plastic itself, or you directly put it into like a thermal process to burn out the plastic, and you would get something like a brown part. It's called a brown part because the temperature at which plastic melts and kind of evaporates away is much lower than the temperature required to weld these beads of metal together. So after this brown part is done, you take it through this process of sintering. Okay, and sintering is basically heating it to a high temperature just below the melting point, where the metal pieces inside the part fuse together. Okay, and then after that, when it comes out, you get the finished part. So as you can see in the diagram itself, the size of the green part and the finished part are much smaller because the plastic has melted away. Okay, and right, so this is metal injection molding, and it's really used a lot in medical engineering applications where you want to have very small precision parts, and it's used extensively there. However, just because of the number of steps required and the complications of using an injection molding machine with metal parts and all that, it makes it slightly expensive. Okay, yeah, so that this is metal injection molding, and I want to see what this is. I think this is like the normal cold chamber die casting. Yeah, so I think this is cold chamber die casting. Okay. So this is the plunger. It goes in with the molten material, and you get whatever part. Okay. Anyway, so beyond that, there are some specific processes, like for example, you can always cast tubes by having this kind of a setup where the mold is rotating and you pour the molten material on it. It coats the surface, remove the excess material, and you would have a casted pipe, and it will be very strong. It will be much stronger than I think it is much stronger than these welded pipes where there is a clear seam, but I'm not too sure. Okay, but anyway, this is a process that is there. You could do this with any kind of molds or designs where the shape is symmetrical. Okay, actually symmetrical. Okay, okay. The other one is centrifugal casting. I think there is another process. Yeah, centrifugal casting is something like this. You have this mold which kind of rotates, and you pour the molten material from the center. The centrifugal force kind of pushes the material into the mold, and it packs the material properly, and you can make like these very, very small thin parts out of this. Okay, these are the same kind of part dimensions, could be same as metal injection molding. Okay, right, so this brings us to the assignment, and I slightly jumped to that, but yeah, I hope this one is mostly casting. Okay, so I ran you through the different processes of a casting, but the responsibility to find out more about it, learn more about it, learn about its capabilities is up to you. I want you to read about the technical details of die casting from the manufacturing engineering and technology book, and I want you to find out more details about investment casting and the process parameters from that book. Okay, so read about that, read about the technical details and what is done. Okay, so that brings us to the assignment, and this time it's a slightly complicated assignment, I think. Okay, let me move myself to I'm at the right place. Okay, so there are two assignments which are linked. So the first assignment, the fifth assignment, not the first assignment, M3A1. Okay, M3A1 is to make a design of a chair which can be made using machining and die casting methods. Okay, so I want you to make the design of a chair which can be made using die casting. I showed you like a benchmark, right? Ross Lovegrove's design is like a benchmark, but you don't need to reach that. That guy is like super duper, but I think yeah, okay, try to reach that anyway. So yeah, so we have the idea is that this is a concept design or concept generation assignment, the fifth assignment. So you have to make 3 concepts of chair designs which can be made using die casting and machining process primarily. You can use whatever hardware and whatever extra few things that are required, but the main process should be die casting. Okay, and the way you present it is important. The first is each concept you have to present it in 3 separate pages at least. Okay, so the first page would be ideation. How did you arrive at that particular design idea? Okay, so you have small lots of sketches, maybe some form exploration, maybe some joinery explorations, and so on, right? The second page would be presentation sketches. Okay, presentation sketches are like larger, more detailed sketches. So what you do is you use whatever methods that you are most comfortable with. You can use CAD, you can use pencil, pen, paper, you can use watercolor, crayons, whatever, right? But you have to make it look nice, but you have to show the details of how this chair looks like. Okay, so maybe try to do multiple angles so that it's more clear. Okay, try to do a perspective kind of a render. Okay, this is most like a render. And the third page is the detailing. Okay, now how do you show detailing? The way you show detailing is you focus on areas where 2 parts are going to get joined. Wherever there is a joinery that is you think that is needed, you zoom into that part and you detail that part. You sketch out, okay, this is let's say a leg, and this is the base, and the way it is joined together here is by this way. These are the 3 screws and this is how it connects, and so on. So these are joineries. Remember, in a product, all the things that go wrong most likely go wrong at the interfaces. Okay, wherever there is a change from one thing to the other. So wherever there is an interface, you think about that area and you sketch the detail of that. So these 3 pages will be there. So in total you will submit 9 pages at least. In 9 pages you will explain 3 concepts. Okay, 3 for one concept, 3 for the other, 3 for the third. Okay, and that's the idea. Now things to remember: all images should be presented in a presentation, and the presentation should be submitted. Try to have a file size of less than 50 MB. Okay, it is very easy to exceed that. If you find it difficult, you can compress the images in a presentation file. Just learn how to do that. Okay, second thing is you can explore anything like digital sketching or traditional sketching or rough CAD modeling also, if you want to show the concepts. Okay, sometimes what happens, you can use a mix and match of these 2 processes. Let's say just the form of the object, you can, let's say if you want, you can quickly model, but to show the detailing, you don't want to do the detailing in the CAD. You take screen grabs or renders of only that part, and you show how the detailing is there through a sketch. Okay, through an overlaid sketch. So you can do digital, or you can print it out, you can sketch on top of it, scan it back and put it in the presentation. Okay, something like that. So you can use mix and match methods of all different types. You need to make clean sketches, and random doodles are only fine for the first page. In the other two pages, it needs to be clean and clear sketches. Okay, so you need to use any tools. You use scales, you use French curves if you are doing traditionally. If you are doing let's say in digital medium, you can explore Autodesk Sketchbook. It has these tools for ellipses and straight lines, and you use these things to make it look better. Okay, don't just freehand all the time unless you are really good. I mean, if you are really good in sketching, you have confidence in your line work, then you are okay. Okay, and if you find it difficult to do perspective sketches, okay, you can do orthographic. Sometimes some designs are slightly more complicated, and doing perspective, it takes a lot of time, so you can do orthographic sketches of these. Okay, so it's that's the fifth assignment. Okay, so these kind of concept of product conceptualization assignment. Things you can try to learn in this fifth assignment is you can try to explore this small workspace in Fusion 360, which is called Create Form. It's by the name Create Form. It's a T-spline workspace. You can go through some of the tutorials that are there. It's a great form ideation, workspace. Okay, so you can try that. You can read and find out about how casting simulation is done. You don't need to do it, but if somehow you think it's very you find it like I can do it, it's not too difficult, you can try to do in your thing. Okay, however, I'm not at all expecting. I mean, if you want, you do, otherwise don't do. And you can try to explore how to render in Keyshot and Blender if you are trying to do digital ways of representing. So this is the fifth assignment. The reason I said and sixth is because the sixth assignment is to make the whole thing in Fusion 360. One of the designs, choose one of the designs, 3 designs, and model it in Fusion 360 with as many details as possible. And the next important thing is to do a simple stress analysis. Okay, so it's called the static stress analysis, and you can do it in Fusion 360. What I want you to answer is, will a person with whatever design that you made in Fusion, can a person of 150 kilos, okay, sit on the chair and nothing will happen to that chair? Okay, or can you make it so that it just barely stands? Okay, if somebody 160 kilos sits, it will break away, but if somebody is slightly lesser than 150 kilos sits, nothing happens as much. So the yield strength, that stresses that are there are just below yield stresses when a person of 150 kg sits. Okay, so this is what I want you to try. You can you use this specific material called 2014 T6 aluminum. Okay, it's there, the properties are there in Fusion. The reason that I'm giving you the material will be more clearer when you explore this. And finally, you need to make a presentation showing the designs and showing the results of the analysis. So how do you do this? I will leave it up to you. So this is a very exploration oriented project. Okay, I will show you how to do a simple stress analysis. Okay, let me open Fusion. Where is my Fusion? Give me a second. Fusion is opening up. Okay, so Cyril, I saw your message, even if you removed. The reason I don't want you to use other software is because you will not be able to do this something called stress analysis. But you can use any software for the fifth assignment. For the fifth assignment, you can use any kind of software, any tools that is available to you. Okay, no restriction. I just need to see how creative you can be when there is a constraint on just the process. Okay, so you have to really understand the process and you have to implement it. So let me just make a very quick model here. Okay, so what I'll do is I will make, let's say, a circle, and let me just give a dimension to it. Let's say this is 200 mm. Okay, and I'll finish it. I'll extrude it to, let's say, okay, 15 mm. Right now I will sketch on top of this, and what I want to make is like a small tower. Okay, can you I hope you can see Fusion. I hope you can see the different menus and all that. Just give me a shout out. Like, don't give me a shout out, just give me, like, tell me if the menus and all are visible and you can see what I'm trying to do. Okay, so I'm making this kind of a design. Let me finish the sketch. I'll extrude it and I will make, let's say, okay, thank you. Okay, so let's say a 300 mm tower like this, and on top of this what I want to do is I'll make a square. I'll make a beam, a cantilever. It's called a cantilever beam. So let me just, I'm making these sketches just to ensure that what did I do? Okay, anyway, so this is equal, and so that means that I can go like this, and yeah, okay. So now I can just give a dimension to this. Let's say I want to give like 80 mm, and let's say this one I want to give like 250 mm. Okay, yeah, that will do. Why is this? Okay, because this, right? So I will say this one is around 30 mm far away from here. Okay, that's it. That's I want to make, and I will just make like a thickness. I will give it 10 mm. Okay, this is my design. This is my chair. Okay, yeah. So now I want to see how strong this is. Right. So what I can do is I can go to this workspace called simulation workspace. Okay. Once I go there, the first thing that pops up is this kind of a dialog box which asks you what kind of simulation you can do, and there are so many that are very interesting. Like, you can do like a natural frequency evaluation. You can see at how the product will vibrate, and what are the stresses because of vibration that happens. You can do like a thermal simulation. If I heat it on one end, how much will the other part heat, and what will be the temperature distribution. I can do an event simulation, and these are fairly advanced and all that. I can do shape optimization, so on. Like, I don't want you to do all of this. I just want you to do static stress. This is like the simplest of all studies. Okay, so what I'll do is select this. So when I click here, it will say blue. Select this, create a study, and yeah, we are in this environment of doing this simulation. There'll be some quick setup guides that are there for you, and there's one which is called nonlinear static stress simulation, which takes the example of a chair. You can take a look at all of these videos to get an idea of how this simulation is done, but I will not show you this. I'll just give you a basic idea. So what I want to do here is I want to test if a person sits, let's say, directly at the edge of it. Let's say there's a load directly on the edge of it downwards of 150 kilos. How will this design withstand the whole thing? Okay, so naturally what I want to do is, first I want to fix this to the ground. So right now this is not fixed. So what I want to do is I'll go here into something called constraints and click on structural constraints. Okay, and I'll select this face, and it will show me a small icon which is like a locked icon. So this means the face is planted flat, and whatever things that I'm going to do, it will not affect that face. Okay, so this is fixed. I will click OK. Okay, now in this small area there's something called study materials, and it says ABS plastic. I don't want you to do with ABS plastic. So what I'll do is I'll hover my mouse over to on this particular thing, and there will be a pencil which pops up. I'll click on that and I'll get this dialog box. It's a little scary, but if you read it carefully, you'll understand everything. It says category plastic, name ABS plastic, component is 1:1 simulation, study material. This material is different than the material we applied during the design phase in the design workspace. Okay, so what I will do is study material is not the same as the model. I will say click here and I will search for what? So I want to search for 2014 T6 aluminium. Okay, and what happens is, because of this, is I can see the various properties of this material. If I click on the properties, I can see. So it has a density of something, let's say 2.8 into 10 to the power 6 kg per millimeter cube. It has a Young's modulus of 72.4 gigapascals and Poisson's ratio, and so many other things that are the properties of this specific material. So I'll say okay. So now this material is applied, and you can see over here it says aluminium 2014 T6. Okay, great. Now what I want to do is I want to say I'll put a load over here. How do I put a load? There's a button called loads. I'll click load and it says what do I want to put? Do I want to put a load? Do I want to put a pressure? Do I want to put a moment? I think some of these terms are known to you. Forget about other things. Let's just take force. Okay, now where do I want to put force? I'll select this and I want to click here. Okay, now as soon as I click here, there's this big blue arrow that comes and it shows me the direction in which the force is applied. I don't want it to be applied like this. I want it to be applied straight down. Okay, so I will angle this and put it at, let's say, 45 degrees. Then it will be straight down, right? Yeah, okay. I can change the angles any which way and apply the force. Now remember, the force is directly being applied only to this edge. Typically what I would want is I would want a small area over here on which the force is applied. Actually, let me just do that. Okay, I don't want that. So I'll go back to the design workspace. Okay, now I can sketch on this. I'll make a small square on top of this. Just give it a basic dimension of let's say 50 mm. Finish the sketch. Okay, and just extrude it just a little bit, like 1 mm. Okay, so it does not change the design as much, but yeah, well, now I go back to the simulation workspace, and whatever setup that I had created, it's still there. Okay, but I have this change in the design, right? So I'll do loads and I will select the face, and now it shows me that the force is applied evenly across the face. Here I'll select 150 kgs, right? So 150 kgs in terms of newtons directly multiplied by 10 ballpark. So 1500 newtons. Okay, so the load is applied. It's held in one place. I'm basically ready. Now in these simulation processes, what you have to do is you have to make something called meshes. Okay, and this is, I actually forget about that. Okay, I'll just go into something called this icon over here. It says pre-check. I'll click on this and it will tell me the study setup has all the information required to continue. Okay, so I'll say okay. If there were some problems, it would give you the details that are there. Now if I can click solve this problem, and it will tell me, it will pop up this whole thing. and it will ask me whether you want to solve it on Adobe's computers on the cloud, or do you want to do it locally. I want to do it locally because my computer is fairly, capable enough. So this needs a lot of CPU, okay, and it's better to do it on the cloud. But here, I mean, I can handle this much, I think. Okay, so I'll do locally and I'll say solve, and it says save the project. I'll say class Asha. Okay, and now it is doing whatever is necessary. Now it will take some time. What is doing? It's preparing the model. Then after that, something else will happen. So yeah, and suddenly it's complete. Okay, it actually takes a little more time. Now everything is there. I close it and it shows me how it is modified. So it gives me some details about the result. So let me move myself on the other side. Okay, right, so it gives me some details. So here what I'm seeing is the safety factor, the factor of safety. So how far are the stresses from the yield stresses of the material, yield strength of the material. Okay, and at the minimum I have 1.3 of factor of safety, and wherever it is blue, the factor of safety is much higher. Wherever it is green or yellow, it's like this. Actually, you know what, just for the sake of showing you the details, I want to increase the loads. Okay, so I'll do finish results and I want to change the loads. Okay, so I'll go to load case and I want to edit structural load, and instead of 1500, let's go with something like a person who is 3000 kilos. Okay, and then I will do the solving thing again, locally solve. Since it's solved fairly quickly, I can wait for that much time. Okay, it's solving. Okay, now I can see some problems. Okay, you can see these red areas. The factor of safety in these red areas are around 0.6 times of the yield stress. If that doesn't make sense to you, you can just take a look at the stresses. Now you'll get more drop down lists over here. I suggest you select von Mises stress. These are theories of stress calculations. We'll not go into this, but just select von Mises stresses, and now you can see where in the model the stresses are very high. At this location it's around 416 megapascal. Okay, and if I had put in more stress, then you would have seen the yield strength of the material also appearing somewhere in this line. Okay, and now it will tell me some recommendations: strengthen the design in the weakest areas, or I use a material with high yield strength and ultimate strength, conduct a non-linear static study for more accurate results, and so on. It will give me this thing, but this is basically done, right? And I can actually see the animation of how this thing deforms with that given load. And yeah, so this is what is actually happening. Do you see? So the question is, should your chair actually be safe to use? No, it's not necessary. You just have to show me what happened when a person who is 150 kilos sat on it. Okay. After all, the modeling, it is not safe. Should it be redone? No, not required. If it's a failed problem, if it's a failed design, it's okay. Okay, I just want you to experience this. Okay, and now I can generate a report from here. I can say, if I do a preview of the report, it opened here in this one. I can show you this. I hope you're seeing. Yeah, so it showed me that this is the analyzed case, this is the simulation result, this is the static this thing, these are the details of the material, this is the load case, this is the loads where you have applied, this is the selected entities where the load was applied. These were some of the stress parameters that were there. So in different models, in terms of first principle stress, what are these? If you want to know, you can see these videos that are there on the internet, but yeah, I'll not explain it in this class. So in terms of safety factor, there are some problems over here and so on, right? So this is a nice result also. You can select each of these images and you can copy and paste wherever required. Okay, so yeah, that is it. That's the simple stress analysis. So you don't need to get worked up by it. Okay, and yeah, just have fun, just learn this something something new about this, and we'll see you in the next classes, right? Okay, so I'll close this and I will go back to the presentation. Okay, so that's the presentation. When are you going to submit this? You can submit after the next module is also over. So in the next module also there will be some 2 assignments, but you can submit it. I'll give you the exact date. So you can submit it before 7th of November. Okay, remember there will be 2 more assignments, but this one you can submit it before 7th of November. So I'll just write it on this presentation, I think. Right, both assignments. Okay. Okay, yeah. So well, where am I? Okay, that's about it for the course, for this class. We'll start off with the next topic tomorrow, same time, and uh, we will not have Saturday's class actually. I have some other things to attend to, so Saturday we'll not be able to do, but tomorrow's class same time. Okay, have fun. I hope you enjoyed the class. Have fun. I'll see you again tomorrow on. Chaitanya is asking, would the next 2 assignments have a 7th November deadline too, or only the 7th limit as before? The next 2 assignments will have 1 week extra time. So 7th के बजाय होगा उसका 7th के बजाय होगा उसका 14th. Okay. Okay. Yeah. Okay, yeah. So thank you everyone for sticking with me for so late. I have some participants shown here. I think others, if they are on their phones or something, it's not seen. But thank you so much. Thank you. Yeah, I'll have to conclude. Thank you. See you guys tomorrow. Have fun.